So what is the slope and y-intercept of 2y plus 4x equals negative 6? If we change this into slope-intercept form, it'll make it real easy for us to tell. So the first thing I would do on this is just get rid of the x's or zero them out, so I'd have to subtract 4x. If I do it to one side, I got to do it the other side. So then I'll drop my 2y here. 4x minus 4x, that zeroes out just like we wanted. And then we got negative 6 minus 4x. I'm just going to switch those so it looks more like slope-intercept form. To be negative 4x and negative 6. Then just divide all the terms by the coefficient of y, which is 2. And now this changes it into slope-intercept form. So the slope, the coefficient of x, negative 4 divided by 2 is negative 2. And the y-intercept, negative 6 divided by 2 is negative 3. So that tells us we got a slope of negative 2. That'd be down 2 to the right 1. And a y-intercept at 0, negative 3. So write the equation in slope-intercept form for a line that passes through negative 1, 5 and has a slope of 10. All right, no problem. In fact, they gave us a slope right here. That's our m value. So all we need to do is solve for the y value. So I use slope-intercept form. Y equals mx plus b. And right there, well, they gave us a slope as 10. Well, they also gave us x and y values in the ordered pair to replace into the formula as well. So the x value shows as negative 1, and the y value shows as positive 5. So I got 5 equals 10 times negative 1 plus b. And then I would take 10 times negative 1, which is negative 10 there. And from here, I'm just going to add 10 to both sides to zero out that negative 10. And yeah, that'll leave us with just the b value, which is all we really want. 5 plus 10 is 15. Negative 10 plus 10 zeros out, just like we wanted. So, in slope-intercept form, y equals mx plus b. In those two boxes, we just found the slope is 10. We already knew the slope was 10, but now we know the y-intercept is 0, 15. So just put that plus 15 right there. And that would be the equation in slope-intercept form. All right, here's our objective. I can write a linear function from any situation. Just take 30 seconds and write that down, please. Now, these linear functions, they're going to look pretty much the same way as the linear equations do. Y equals mx plus b stuff is just, now we may see, I don't think we see it today, but since we're in the functions unit, you may just see it as f of x equals mx plus b. But nothing else changes. Remember that the y value now is just the f of x. And something else we need to remember today is the dependent variable is always the y value, or the functional value right here. And then the x value is always independent, because it's going to ask us about the two. All right, yeah, the y value we can see just from the way this equation sets up, that you would solve all this stuff here first, and that would then give you the y value. So that's why it depends on x. The x is the value that's changing. The m never changes. That's the slope or the rate of change. And the y-intercept never changes as well. The only thing that's changing is the x. And if you need help with that stuff, like looking at tables, remember it's always going to set up like this, x and y like this. So then you'd know the left column is the independent variables, and then the right column is always the dependent variables. So yeah, we'll identify the dependent and independent variables in these situations, and then we'll make the determination if they're linear or not. If they are linear, we'll make the function for it, just y equals mx plus b stuff. So number one, an object is dropped from a bridge into the water below. The graph below shows the height of the object in feet with respect to time in seconds. Consider the relationship between the height of the object and the time. And just from the wording on this one, we can see it says the relationship between the height of the object and time. But up here, yeah, it says the height of the object with respect to time. It's always y with respect to x. And the other thing we've talked about already in this unit is this one's looking at time. Whenever we see time, we should know that it's independent. We've already marked it with x. There's another way to tell, though, because time is showing in the graph right here as the x-axis. So that means we know time is independent. and then the height of the object will depend on how much time has passed. And finally, is this data linear? Just looking at the graph, we should be able to make that distinction. This one's very curvy. Well, not very curvy, but it's curvy enough. So the answer is no, not linear. You could say it's curvy. You could say it's just not a straight line if you want. So that's how we can tell on graphs if it's linear or not. But remember, if we're looking at a table, we need a constant rate of change. If we're looking at an equation, then we should just see it pretty much in slope-intercept form. But also, like we talked about last time, in order for an equation to be linear, it can't have any x's with absolute values, square roots, or exponents, and x can't be in denominators as well. So this one says, if yes, construct the function, but it wasn't, so we're not going to worry about that. All right, number 2, Owen is earning pennies each day that he makes his bed in the morning. On the first day, Owen's mom gives him 2 pennies, which is shown in this modeling right here, this chart. On the second day, Owen's mom gives him 4 pennies here. So we got 4 boxes. Looks like each box is a penny. And then on the third day, 6 pennies, and on the fourth day, 8 pennies. And so on. So this pattern would continue in this way. Owen makes his bed every day, and this pattern continues. The model below shows how many pennies Owen earns each day. Each box represents 1 penny. Consider the relationship between the number of pennies received on a given day and the day number. So we're looking at 2 different quantities. We're looking at the number of pennies and also the day number. We just got to figure out which of those 2 is independent and which one's dependent. So you could just ask yourself, since we know what 2 values we're comparing, well, we know how many pennies Owen gets depending on the day, or will we know the day number depending on how many pennies he gets? Well, one has to come before the other, and yeah, the day number is going to happen, and then the mom will decide how many pennies to give him. So yeah, it looks like the day number is independent. And we should know that the day is independent because it's a form of time, right? And then the dependent variable is the number of pennies. So is the data linear? Well, we're not looking at a graph, although you could say, yeah, I think I could graph this pretty quick, and that'd be fine. But I can look at the modeling on this, so we can find the rate of change. And that's all we need on this is rate of change. It's a word problem, so it's rate of change. You could still call it slope, though, if you'd want. And so remember that we're looking at this as a ratio of y's to x's. So I'd say, okay, the y, that's the pennies, right? From day 1 to day 2, we get 2 pennies right there. So that's 2. And that would be an addition of 1 day. So 2 pennies. We can put a P there for 1 day. Now, if it's linear, all the ratios will be the same. So from day 2 to day 3, that's 1 day again. So as a ratio, that'd be 1 in the denominator. And another 2 pennies there. So it increases. The change goes up by 2 pennies for another day. And these are equal. Those are the same ratios. But we need to check the final value that they gave us. Another day. So is this that's a 1 in the denominator for another 2 pennies for old Owen. So yeah, these 3 ratios are all equal. And so yeah, this one is linear. Now keep in mind, if by chance you got like a 4:2 ratio like this, it's still equal, because if you were to simplify 4 over 2, then it would be the same as 2:1. Or you could scale 2:1 up to 4:2. So it is linear, so we're going to make the function for this one. Now remember, we'd usually write this as y equals mx plus b. And we're really just filling in these 2 boxes. Well, we just found the rate of change. That's m, which is 2 pennies for 1 day. But just simplify it for the equation. It's just going to be 2. Now the y-intercept would say how many pennies on day 0 Well, if he's getting 2 pennies every day, that means we'd have to go back 1 day, right? To go to day 0. Which means you'd have to take away 2 pennies, so that'd be 0 pennies. Day 0 equals 0 pennies. So you could put plus 0 right there if you'd like, but it's usually good to just simplify that. Now since we are looking at making this a function, you can keep it y equals 2x, but since we know it's a function, I'm going to change that to f of x, even though on the assignment it may not do that, okay? So that's f of x equals 2x, and that would be the function. So going back to that same problem, Owen's earning pennies. We're going to look at this a little different. We're going to compare total number of pennies to the day number on this one. All right, so let's go and put the day numbers on this. I'll start with day 0, even though the last one didn't really include it. We kind of forced it in there. We'll go up to day 4, it looks like. Got 5 boxes there. Now, if we look at the information that was given on that last slide, of course, on day 0, to get 0 pennies. On day 1 is 2 pennies. On day 2, 4 pennies for Owen. Day 3 is 6 pennies, and day 4 is 8 pennies. Okay, so this is how many pennies he gets at the beginning of the day. But what we want to find out is how many pennies he gets as his sum, right? So how many total pennies does he get? So what we're going to do is let's figure out how many pennies he has, and then just add it to how many pennies he gets, right? So the sum of pennies on day 0, yeah, you just have 0 pennies, of course. On day 1, you'd have 2 pennies, but would add the previous day's sum, which was 0, so that's just 2. On day 2, we're going to take those 4 pennies that he just got and add those to the 2 pennies that he already had. That's 6 pennies. On day 3, he'll get 6 more pennies to add to the 6 that he already had, so the new sum is 12. He'd have 12 total pennies on day 3. And on day 4, he's going to get 8 more pennies to add to the 12, so that gives him a total of 20. Now that we have this, and we're really only comparing the sum of the pennies to the day number, I'm just going to get rid of that middle column so we don't get confused by the information that was given there. All right, so we've completed the table. Let's make the determination on dependent and independent on this one. Well, remember, the left column will always be your x's, and the right column should always be your y's on this stuff. That's a y right there. So independent here, it looks like it's still the day number. And dependent, that's the sum of the pennies. All right, and then is the data linear? If it is, then we'll make a function for it, but if it's not, then we won't worry about it. So let's find the rate of change on this. So from day 0 to day 1, that'd be an increase of 1 day. So as a ratio, it's over 1. And how many pennies did it increase? It goes up by 2 pennies. So that's a 2-to-1 ratio, just from the first set. And then from the second set, he's going to get an increase of 4 pennies for this 1 day. So we got a 2-to-1 ratio and a 4-to-1 ratio. Are they equal? No, they are not. So this one is not linear. Now, if we had found that it was still a 2-to-1 ratio, we'd have to check the other values as well to see if it's linear. But yeah, just because the first 2 weren't, we can stop right there and make the determination that it's not linear. So when you get into 9th grade math, I believe they go over how to write these equations. But for right now in 8th grade, we're not worried about this stuff. All right, carbon-14 has a half-life of 5,730 years. The table below shows the amount of carbon-14 that will remain in a given number of years. Consider the relationship between number of years and amount of carbon-14 remaining. So independent and dependent on this stuff. Again, since they gave us a table, x is on the left, y is in the right column. So independent right here, that'd be number of years. And dependent looks like it's milligrams of carbon Yeah, sure, we can put carbon 14 if we want. Well, then we just got to see if this is linear or not. Let's see. So we'd say, okay, you got 8 to 4 milligrams. That means it goes down 4 milligrams right there, okay? And you're going to increase the years by 5,730, okay? So right now as a ratio, that's a -4 to 5,730 ratio. I'm going to put that in the calculator and see what that looks like simplified. So -4, I'm using the N over D button, 5730. It gives me a really ugly decimal. It's like -0.0000698. Yeah, I'd stop there. But let's see what the next one shows, right? So this one now, it's going to go down 2 milligrams. And so then to find out how many years that is, just do 11,460 minus 5,730. And you'll see that's an increase of 5,730 years, okay? So as a ratio, that's a -2 to 5,730. And when I put this into the calculator, I get -0.0003. And that's enough to see that these two are not the same. Of course, you could have used the denominators, right? You're comparing the 5,730 with 5,730. The numerators are different, so these are not equal, which means this is not linear. And it's for the same reason as that last one. It's because the rate of change is not equal. So yeah, that's not a constant rate of change. Steve is lifeguard at a local community pool. Each day at noon, he records the temperature and the number of people in the pool. You think the relationship between the temperature and the number of people in the pool is linear? Why or why not? Now, there's a few different ways to go about this one. I'm going to say no. It's not linear. And that would specifically be because, while the temperature may be the same even, that means that the number of people in the pool would have to be the same, but depending on the day, of course, you'd expect a different number of people. And also the time of year. But there's other factors that may affect the temperature as well. So if it's colder in the building or if the water's colder, maybe you'd expect a lower number of people. So there may be a relationship there, but to say that it's linear, so it's consistently the same each time with the change in temperature and change in people, yeah, I highly doubt that. If you said linear because, well, it's at noon each day, so the temperature of the pool should be the same. So you'd expect the same number of people every day because the same number of people go to work or come to the community pool. That would work, but I doubt that's very consistent there. All right, let's put these cyclists in order from slowest to fastest. So we're looking at speed on this one, slowest to fastest, and they even said X is time and Y is meters traveled. So we're actually looking for distance to time ratio because that will give us speed, right? It's always distance divided by time. That's how we figure out rate, or in this case, the rate is the speed. Cyclist A, if I want to find his speed, I'd say, well, what distance does he go? You go one distance, that's meters. For 2, that's 2 seconds right there. So 1 meter in 2 seconds. Again, we see another 1 meter in 2 seconds. So that's a constant rate of change. So you could say, well, that's a 1 meter to 2 second ratio. All right. If you wanted to compare these each with 1 second, you could. You could say, well, how far would he go in 1 second? That's a 0.5 meters. Okay, so I'm going to be using the per second ratio to figure out the speed for each of these. So that's cyclist A. Cyclist B is Bob cycling 12 meters in the past 6 seconds. So again, as a ratio, it's meters to seconds ratio, and it's showing 12 meters for 6 seconds. I just divide those both by 6 to figure out the distance Bob goes in 1 second, and that's in meters. 12 divided by 6 is 2 meters per second. And right off the bat here, we can see that Bob, cyclist B, is going, well, a lot faster than cyclist A. And we are going to need that information, and since we're trying to determine who's going from slowest to fastest. Cyclist C right here, it gave us the rate of change as the slope in this equation. It's a 1-to-3 ratio, so that's 1 meter per 3 seconds. Again, I would want to see this in a per second ratio, so I do 1 divided by 3, which is, I'm just going to put this to the 10th, 0.3 meters per second. So from these three that we have, cyclist C is actually going the slowest so far. For cyclist D, this is a graph, so I'm going to need the slope formula on this one, which is still the rate of change. But we got these two ordered pairs, right? We got this y-intercept here at 0, 0. And then the other ordered pair I see on this one is this one right here. It's 3, 2. So I put these two ordered pairs in the slope formula, 3, 2, and also 0, 0. And I can type this directly into my calculator using the N over D button. It's going to show 2/3. So that's 2 meters for 3 seconds. But again, I want to see this for 1 second. So divide them both by 3. 2 divided by 3. It's going to be about 0.7 meters per second. And yeah, that's an estimation, but that's okay. But from this information, I should now be able to tell who's going slowest to fastest. So the slowest one that I see is cyclist C. The next slowest is 0.5 meters. That's cyclist A. The next slowest is cyclist D at 0.7 meters per second. And yeah, cyclist B is going much faster, more than twice as fast as any of the other three cyclists. So these are listed in cyclists from slowest to fastest, CADB. All right, 4 families are meeting up at Disneyland. Each family starts driving from home. The representation below shows the distance each family is from Disneyland over time. And yes, X is time in hours, Y is distance from Disneyland. That's good to know. Assume the families drive to Disneyland at a constant rate, which makes this very convenient. So part A, B, C, D, E, and F. In order to figure these out, we need to figure out their speed, but also the y-intercepts. A and B are about y-intercepts. Which family lives closest to Disneyland and which family lives the furthest. That's going to be our y-intercept. Because the y-intercept for these ones is going to be at 0 something, like this. And the B value, the y-intercept, will tell us how far away they are. And the speed in these ones, we're going to see that they're negative because they're getting closer to Disneyland. And the speed, of course, is the slope or the rate of change. So that's parts C and D. That's talking about speed because both of those are rates. Speed is always a rate in distance to time. In this case, it looks like we're dealing with miles to hours ratio. And then part E and F is kind of our x-intercepts. We'll just see who gets there first, which means the distance would be 0. We'll get to those. So family A, I would actually change the way this equation looks so it's in slope-intercept form. Y equals mx plus b, and we can see the m here is negative 55, negative 55x, and then would have positive 95. Okay, so I just changed the format a little bit. I just switched the two terms. But this also tells us the rate they're going, m, which is 55. I should put this down here, 55 miles per hour. And I'm not making that negative because that's the speed they're driving at. It's negative. It's a negative slope because they're getting closer. And then, of course, the y-intercept here, that's going to tell us how far away they are from Disneyland to start out with. So that'd be 95 miles away. All right? So we assume this is how far away they live. That's okay. Part B says they live 120 miles from Disneyland. That, by the way, is the y-intercept there. So that'd be 0, 120. And they're driving at 60 miles per hour. Well, that's already the slope or the rate of change. It's 60 miles per hour. So just from these two families, we can see that family B, they're traveling faster by 5 miles per hour, but they also live farther away by 25 miles. But we need the other families as well. So family C, in fact, the table gave us the y-intercept, so that means this family lives 80 miles away. And the table will tell us the slope as well, or the rate of change. So they're going to go 80 to 5, that's 75 miles. And from 0 to 1.5 in hours, that's 1.5 hours. So as a ratio, it's negative 75 to 1.5. And if we simplify this, it'd be 50 miles per hour. And again, you can do that in the calculator. Just do negative 75 divided by 1.5. So family C, we see their speed and how far away they are. And in comparison to families A and B, they're going, looks like the slowest. Yeah, we don't really need the negative on that, 50. They're going the slowest, but it looks like between the three families, they also live the closest. So let's look at family D then. Family D, we have a y-intercept. That's just where the line goes through the y-axis. That's at 0.45. And then the other ordered pair that I see is this one right here. That's at that's 1 hour and 5 miles. All right, but the y-intercept, yeah, that tells us they're 45 miles away to start. So that's probably how far away they live. And then after driving for 1 hour, they're 5 miles away from Disneyland. Okay, so to find the slope on this one, we're going to use the slope formula. And we got the ordered pair 0.45 and the ordered pair 1.5. So this would give us the rate of change. That looks like it's negative 40 to 1. That's 40 miles per hour. So they're traveling at 40 miles per hour. And we can also see, well, I guess we'll get to that next part. So just from this information, we should be able to answer those first 4 questions at least. So which family lives the closest to Disneyland? So yeah, family A, that's 95 miles. That's closer than family B, but it's not as close as family C. They're 80 miles away. Family D, though, they're only 45 miles away, so they're the closest. Family D is the closest. Family that lives the furthest, that's B, they're 120 miles away. But speed on this one, that's our M, or the rate of change of the slope. And yeah, it looks like the family going the fastest here is 60 miles per hour. We got 55, 50, and then 40, so yeah, 60 is the fastest. And that also is family B. So they are going the fastest, but they live the farthest away. And then which family's traveling the slowest? Yeah, that's family D right here with 40 miles per hour. So family A had 55 miles per hour. Family B, 60 is the fastest, and then 50 for family C. So 40 miles per hour is the slowest. So who will get there? Who's going to get to Disneyland first? Let's go through each family and figure that out. So family A, I'm going to use the equation to solve this one. That's y equals negative 55x plus 95. When I solve this, it will tell me how far or how long it's going to take them. Well, to figure out how far they are from, or how long it's going to take to get to Disneyland, that means their distance would be 0. Once the distance is 0, then they're at Disneyland, right? So I'm just going to solve this equation. I'm going to subtract 95 from both sides. It's just a 2-step equation. So I got negative 95 equals now negative 55x, which we dropped. 95 minus 95 is 0. That's good. Divide both sides by the coefficient of x to make that a phantom 1. And x, that's how long it's going to take. 95 divided by 55. I'm going to use my calculator for that. Got 1.72, 1.73-ish. I'll just put 1.7 hours. So that's family A. It's going to take them 1.7 hours to get to Disneyland. Family B, I can do the same thing. because we have the slope and the y-intercept on this one. The slope was 60 miles per hour. You can even put negative 60 to show they're getting closer. And they're starting at 120 miles away. But again, we want to know when that y value is going to be 0, because that's the distance from Disneyland. Well, subtract 120. Not everyone needs this. Some of you know it's just 2 hours, and that's fine. So it's a negative 120 equals negative 60. That's a negative 60x. Divide both sides by negative 60. And x, that's going to be 2 hours. So family B is going to take 2 hours. Family C, we can do the same thing with the equation stuff. So on this one, y equals mx plus b. Yeah, the m there is negative 50, because they're getting closer. But again, we're looking at how long it will take for the distance to be 0, and the y is distance. So solving this one, subtract 80 from both sides. Divide both sides by the coefficient of x, negative 50. That tells us x, just put this in the calculator, you get 1.6 hours. So family C is looking at 1.6 hours to get to Disneyland. Family D is not so bad because this is a graph. We're just looking for where the distance is 0. That's the x-axis. That's right here. I'll use orange. That to me looks like it's about 1.1 hours. And we can't estimate that because the other values aren't even close. So looking at these times for how long it will take the families to get there, who's going to get to Disneyland first? It looks like family D will, even though they're going the slowest. Part of that, of course, is because they live the closest. And then who's going to take the longest? Yeah, it looks like the 2 hours for family B. That's going to be the longest. So family B, again, they're traveling the fastest, but because they live the furthest away, yeah, it's going to take them the longest to get there. All right, this one's just asking which bathtub will empty first. So bathtub A starts with 25 gallons and is draining 1.5 gallons per minute. So what you can do on part A, if you wanted to write the equation, you could, but you could start, if you wanted to, with 25. And then you say, well, take away 1.5, that'd be 1 minute, and then another 1.5, that's another minute, 1.5, and just keep going from there. Or you could take the number of gallons, which in this case is 25, and just divide it by the rate. Okay, because this one's, it's asking which one will be first, so that's like a time over distance kind of thing. No, it's distance divided by rate kind of thing, yeah. So I'm just going to take 25, and yeah, this is just repeated subtraction, which is kind of what division is, and divide it by 1.5. This will tell me how long it's going to take bathtub A to drain. 25 divided by 1.5, I get 16.6, but this time we're looking at minutes. In fact, I'll just round that to the 10. So this one will take 16.7 minutes. Let's look at bathtub B. So we see looks like every 3 minutes, it's going to drain off 5 gallons. So right here at 6, we'd say, well, take off another 3, or add another 3 minutes. That should be minus 5 right there. And then take off another 5 gallons, right? So that'd be 10 gallons. Take off another 5, and then another 5, and you'd get to 0. So that would be another 3 minutes from 9. Should have been a 9 instead of a 3, and then another 3 minutes. That'd be 12. Another 3 minutes would be 15. So it's going to take 15 minutes. So just between the two that we've done, bathtub B is going to empty first. And bathtub C, this one we can see it has a y-intercept at 25. So it's going to start with 25 gallons. And then you probably want to find the rate on this one. Looks like it's this value right here. That's at 3 minutes. There is 21 gallons left. So That's a 0.25 over here though. So to find the rate of change on this one, use the slope. Yeah, that's better. 0 minutes for 25 gallons. And then the other one was 21. No, I did it backwards again. It's 3 minutes for 21 gallons. So this one's draining off 4 gallons every 3 minutes. 4 gallons per 3 minutes. So we can take how much they start with, 25, and just divide it by -4/3 if we wanted to. I don't know what that is, but the calculator does. It's 18.75. So this one's going to take 18.75 minutes to drain. And yeah, now we can see that bathtub B, that's going to be the fastest. Why? Because, well, we did the work for it. That's good enough for me. Of course, you could say, I mean, they all started with 25 gallons, but bathtub B has the greatest rate of change, right? It's going down to 5 gallons every 3 minutes. Again, that's a 1.7-ish gallons per minute. This one was showing 1.5, and then this one showing 1.3. So yeah, bathtub B, they all start with the same number of gallons, but bathtub B is draining the fastest. So for each problem, circle the representation that has the greatest rate of change. Put the star by the representation with the y-intercept, greatest y-intercept. Assume all representations have a constant rate of change. That's good. So 9, let's identify first the rate of changes, all right? So 9 has a 3.5 rate of change. It's just the coefficient of x. That's the slope. In the table, it's showing that it goes up, looks like 12 to 4. And 12 to 4 would be 3, which is less than 3.5. And then in the graph, I won't use the formula for this one. I'm just going to use the rise to run. So that goes up 1, 2, 3, 4 boxes. And then to the right 2 boxes. So that's a 4 to 2 ratio, which is 2. And that's even less than the other 2. So it wants to circle the representation with the greatest rate of change. That's the equation. And then the y-intercept on this one, it's given right here at 0.2. And so for the table, I'd say, well, let's go back 12. Well, I wouldn't go back 12, actually. I know it's a 3 to 1 ratio right here. So I'd have to go back 3 and then back 1. And the x, that'd be 0. Back 3, that's 5, so that's a 0.5 y-intercept. And yeah, the graph, we can see the y-intercept right there at 0.3. So it looks like the table has the greatest y-intercept value. Now let's do the same thing with 10. Let's find the slope. First, we'll compare the slopes or rate of changes. So there's one ordered pair. Looks like it's this one as well. So it looks like it goes down 3, 7. And then to the right 2, that's a -7 to 2 ratio for the slope. And then in the table, I got down 6 to the right 2. So that's a -6 to 2 ratio, which is just -3. And then in this set of ordered pairs, we got 0.3. And then 2, -5. When you put this in the calculator, what does that give you? 8 over -2, that's -4. So we have these rate of change. We got to be careful on this stuff because this one's -3.5, this one's -3, this one's -4. The greatest of those values, it would be the lowest negative, which is this -3 right here. So it would circle the table. This one has the greatest rate of change. I guess we got to be careful on that one. If we're looking at the changes, though, this going down by 4 would be greater than this one. So it depends on how it's worded. But I'm just comparing the numbers directly and saying which one's the biggest. -3 is the biggest. And then we got the y-intercept. This one gave us the y-intercept, the table gave us the y-intercept, and the graph shows the y-intercept at 0, 3. So the biggest of those is actually the 0, 4 right there. This one gets a star. On number 10, the table gets the star and the circle. Oh, that's very nice. All right, and there's our objective. I can write a linear function from any situation. And we did a lot of comparing those functions as well, okay?